All right, so last term we finished up talking about substitution and elimination reactions. This term we're starting the chapter off by essentially doing the reverse of an elimination reaction, and this is known as an addition reaction. So an addition reaction is essentially an elimination reaction in reverse. All right, and I'll show you guys kind of what I mean by this, and we'll do a little bit of review too. Okay, so in this reaction, let's say I've got a bromine here, and I've got a really, really strong base. I'll indicate that by having a negative charge. Is this going to be an E1 reaction or an E2 reaction if we have a strong base? E2, okay, so we know it's going to be E2 because we've got a strong base. And we know with an E2 reaction, we're going to make an alkene. We're going to make our conjugate acid, and then bromide's going to pop off as our leaving group, right? I don't have the full reaction pushing arrows there, but you get the idea. Let's take a look at addition reactions. Addition reactions involve an alkene plus some other group, and I'm just going to call this group generic XY. What we're going to do is we're going to add both X and Y across the double bond. So it doesn't matter where you put the X or the Y because they're just made up at this point. But you can see in the top one, we're going from an alkane to an alkene. Where in the bottom one, we're going from an alkene to an alkane. All right, so let's think about this too in terms of entropy. Which one is entropically more favorable? The elimination reaction or the addition reaction? The elimination reaction is entropically more favorable, right? So we're creating more moles of product than we had starting material. So is that going to be favored at high temperature or low temperature? High temperature favors disorder, right? So we saw in elimination reactions, they oftentimes were done under high heat conditions. If we look at addition reactions, they're essentially the opposite, right? We're going from 2 moles of our starting material to 1 mole of product. In this case, heat is your enemy. In fact, you want to run these reactions very cold to favor the formation of 1 mole of product and disfavor the elimination reaction. The interesting thing with addition reactions that we have to pay attention to is pi bonds are now acting as our nucleophile. So in addition reactions, pi bonds act as your nucleophile. It's a little bit different, but if you remember all the way back to last term, I said that nucleophiles are any molecule that are electron rich, right? A pi bond, we've got p orbitals that are occupied with extra electrons. Those can act as a nucleophile as well, and we'll see this all throughout the chapter. Does that make sense? We'll start off with an easy one. The first reaction we'll cover is hydrohalogenation. And in hydrohalogenation, you're going to use some sort of strong acid. So for this one, I'll use hydrobromic acid. You can use hydrochloric acid or hydroiodic acid. The only one you really don't see is hydrofluoric acid. Hydrofluoric acid is a really weak acid, so it doesn't really do much for this type of reaction. So let's make a note of what's going on here. We've got our nucleophile. We've got HBr, which in this case is both our acid and our electrophile. And it's important to remember that HBr, we've got a net dipole going towards the bromine. It's very electronegative. So in this case, our nucleophile is going to attack this proton, and then we have to kick off bromide in order to prevent an octet rule violation, right? So now we've got 2 potential products. The question is whether or not the proton will get delivered to that central carbon, and we'll have the carbocation out here, or will we have the proton on that right carbon and our carbocation in the center. Which one do you think is more likely?
The right.
The right one? Why is that?
More carbocation.
Yeah, if we look at this one, this is a primary carbocation. This is secondary. We said anytime you form a carbocation, you want to form the most stable carbocation, right? So this reaction, you don't see any of this intermediate. You only observe the more stable carbocation as your intermediate. And we kicked off bromide, so that's still floating around in space. So this bromide can now act as a nucleophile, attack that carbocation, and now we've got the hydrogen on the less substituted carbon, and the halogen, which in this case is bromine, on the more substituted carbon. So this would be our product. So let's make some notes for this reaction, because there's a fair amount going on. So always form the more substituted, or sorry, more stable carbocation. So we said last term resonance is the best, followed by tertiary, secondary, and then primary is really crummy. So try to form the most stable carbocation that you can in that first step. And then the second thing is this is referred to as Markovnikov addition.
What was that?
I'll write it down. So Markovnikov addition. And this is named after the scientist who basically discovered the fact that the bromine that's added in is always getting added into the more substituted carbon. All right, so that's an important thing to remember is that new term. Yep.
So, can't you? I know that with a BR and then well, the structure on the right side there. It's I see the CH2 and then a bond to an H. Can't you go for a shortcut and say CH3?
You can write CH3. I just showed the one proton there to show where that specific proton was being added to. You can show all the hydrogens or none of them if you want, because it is von line structure. All right, and then the last thing to pay attention to that didn't matter in this case is you have to watch out for stereoisomers. All right, if we look at our product here, we don't have any stereocenters in there, so we don't have to worry about it at all. But if you are forming a new stereocenter, you have to worry about getting both the R isomer and the S isomer out. Yep?
Sorry, it's a little while back. Did you say that it's all halogens except for fluorine?
Yeah, so all of these acids that we use are HBr, HCl, HI, but not HF. HF we really don't observe for this reaction. Yep. All right, so let's take a look at an example where we do have a set of stereoisomers, and I'll ask you guys to help me with this reaction. So let's do this example. So let's say I have this alkene, and I have HBr as my acid. Let's go through and draw the full mechanism and pay attention to stereochemistry for this. So I'll give you guys a minute to work on this, but check with your neighbor and see if you're coming up with the same mechanism, most importantly, and then the same product or products. I'll get us started with some intermediates here, and then we'll fill things in. All right, so let's start with the arrow pushing. We know that the nucleophile is going to attack in. We're going to kick off our bromine. That means that we could have the hydrogen add to the right side, in which case you can imagine your proton coming off there, right? Or we could say maybe it's on the other side. Which of these do you think is a more likely intermediate? The one on the right, right? Because this one's a secondary carbocation, which we know is less stable than tertiary, and we just said that anytime you do this, you want to have the more stable carbocation. Make sense? Okay. Now we've got bromide floating around still, and bromide we know can attack into this carbon. However, what's unique about that carbon with the positive charge? It's trigonal planar, right? And we have a p orbital sticking both up and down out of that carbon. So it can do a top side attack, so I'll just write top. Or it can do a bottom side attack. It really has no preference in this case. And so we can imagine maybe we have one product where the bromine, when it gets added in, is a wedge, which means that methyl group must be a dash. Or maybe we've got one where the bromine is in that dash position, which means that the assumed methyl group there must be a wedge, right? What's the relationship between our two potential products here? They're enantiomers, right? We've got mirror images of one another. Does anybody remember what we call a 50-50 mixture of enantiomers? Racemic. So in this case, it's a racemic mix. Will this be optically active? Meaning if we put it into a polarimeter, will it rotate plane polarized light? No, because it'll cancel out, right? One will twist light one way, the other will rotate it the opposite way. If you've got an equal amount, they just cancel each other out. So this is a perfect example of that. All right, let's take a look at another example.
Well, you always have a racemic mixture when it was a mix of enantiomers, right?
Yeah, if you are forming a mixture of enantiomers for this type of reaction, it will be racemic. Okay, so let's take a look at another example. And this one's going to be a little bit more challenging. So see if you can spot the tricky part with this. And I'll give you a hint. It involves something we saw a lot of in first term with carbocations. I'll get us started with some intermediates here. So let's get started with our arrow pushing. We know we can do the same thing we've done before. We can have a proton add to the more substituted carbon, meaning right there. Or we could say maybe it's coming off that less substituted carbon. Which one's more likely?
The left. I mean, right.
Yeah, your other right. So secondary versus primary. We know the secondary one's a lot more stable. All right. Now, is bromine going to attack straight in? No. What might happen before bromide gets a chance to attack in? A rearrangement. So we saw last term, secondary carbocations, if they have the option to, can rearrange. In this case, we're going to move this whole methyl group hanging off over here, over to that interior carbon. And I'm going to leave off the blue proton just to keep things simple at this point. That means that we now have formed a tertiary carbocation, which we know is a lot more stable. Oop. Now we've got bromide floating around. This bromide we know can attack in. It can attack in from the top face or the bottom face, but does it matter? No, because we aren't forming any new stereocenters. There are no stereocenters in this molecule, so we don't need to worry about it. People will often ask me too, they'll say, if there's no stereocenters, do I need to show dashes or wedges? No, you don't have to. It doesn't really show you anything because it's not an R or an S. So quite often people will just show it in regular bond line notation. This is a big problem with hydrohalogenation reactions. Often, if there's a potential of a rearrangement, people just avoid this reaction altogether because it's very, very messy. In fact, the bromide can attack into the secondary carbocation before rearrangement or the tertiary carbocation after. So you end up with this giant mixture of products that's a pain to clean. There's a workaround that we'll talk about tomorrow where you can use mercuric acetate, but we're going to leave that until tomorrow. But let's make a note. This reaction is avoided if rearrangements can occur. All right, and I'll show you guys one oddball thing too before we move on to our next reaction. This is anti-Markovnikov hydrohalogenation. And what does it mean with Markovnikov addition again? Yeah, so Markovnikov addition, we said the halogen adds to the more substituted carbon. Anti-Markovnikov, on the other hand, probably means it's going to the less substituted carbon. So let's take a look at that. And I'll just do a compare and contrast here. We said with HBr that the bromine prefers to be there. So this is Markovnikov. However, when this chemist was studying this reaction, he noticed quite often when they did this experiment that the bromine wouldn't add to that position. It would add to the less substituted carbon. And in fact, they determined that what was causing this was an impurity in their hydrobromic acid. Specifically, it was a peroxide impurity. So I'll just abbreviate that ROOR. R can be any alkyl group. So a bunch of different peroxides can set this off. But this tends to favor anti-Markovnikov addition. So this is kind of a neat trick that you can use to determine where the halogen will go off of. Anytime you see peroxide around, the thing being added will add to the less substituted carbon, and we'll see another example of that later on this week. The good thing with this is you don't need to know this reaction mechanism. This mechanism involves radical pathways, which we haven't talked about radicals yet. We will talk about radicals in chapter 11, and we'll come back and review this reaction in more detail. Does that make sense? All right. So in both of these reactions, you can see we added a halogen on. There's another reaction where you can actually add two halogens across the pi bond too. Do you guys remember doing that last term with the Stilbene lab? So now we get to go back and review that mechanism a little bit. I'm going to go a little out of order from what's in here. And this is just referred to as a classic halogenation reaction. So let's take a look at the classic halogenation reaction. Typically, this is done with bromine, like we saw in our Stilbene lab. And let's try to determine what's going on here. All right. So we know that our pi bond, like I said before, can be a nucleophile. So I'll just abbreviate that nucleophile, which means that our bromine must be our electrophile. It's a little bit confusing because you might say, well, there's no dipole in bromine, right? There's no net dipole in any particular direction. However, it's such a large molecule that it does have a fair amount of that dipole induction, instantaneous dipole, also known as van der Waals forces or London dispersion forces. So it's decent enough. So in this reaction, this pi bond is going to attack bromine. And then one of the lone pairs from bromine will actually attack the other side. And then we'll kick off a bromide. So it looks a little bit weird. And when we do this, we end up forming a three-membered ring. Sorry, that looks messy. Where bromine is in the center. And bromine now has a positive charge. And bromide is off to the side. This is referred to as a bromonium ion.
Very stable though?
No. Why do you think it's not very stable? That's a good point. The bond angles look all wrong, right? If we look at those carbons in the three-membered ring, those are sp3 hybridized carbons, but we're pushing them into 60-degree angles when they want to be 109.5. That in bromine doesn't like having a positive charge. Everything about this looks and feels wrong, but we'll talk about why this mechanism is correct. All right, so now when the bromine attacks, you can think about it this way. This bromine, because it's super duper unhappy, is sucking all this electron density away from that central carbon right there. So this carbon right there is really, really, really electron deficient. And so this bromide can attack in, slingshot this open. You now have two bromines where there used to be a pi bond, and the bromines are going to be opposite of one another. This is referred to as anti-addition. All anti-addition means is that the two bromines were added to opposite faces of that original pi bond. So one is on top, one is on bottom. All right, let's take a look at the alternate pathway, and we'll try to make sense of this. And this is one that I see all the time with mechanisms that students put on exams and quizzes, so we'll disprove it once and for all. Okay, so let's say I've got this compound and I've got bromine. We would think, you know, why doesn't it just do what we saw before with a hydrohalogenation reaction where we just form a carbocation, right? For a lot of students, that would make sense. And then at this point, we could have bromide float around, and it could attack from the top face or the bottom face, just like we said before. So I'll make this ethyl group a wedge, and then a dash for one of these. And then for the other one, I'll make the ethyl group a dash and the bromine a wedge. This is not the correct pathway. So we'll put this with 3 exclamation points and underline it a few times. The reason for this is if we look at this one, this wasn't specifically anti, right? It could have attacked from the top or the bottom face, where the top pathway said, no, it's specifically anti-addition. Experimentally, they're always going to be on opposite faces of that pi bond, and it's very important to pay attention to that. So it looks weird to draw this bromonium ion, but I do like to show this example because intuitively this feels right, but experimentally we know it's wrong. So please don't show carbocations anytime you have a halogenation problem. You should always show that funky three-membered ring. Does that make sense? All right, so let's take a look at an example one. This one's going to be a little bit harder. And I'm going to abbreviate all of the groups coming off here. I've got an ethyl group there, so ET, ME for my methyls, and a hydrogen here. And right now I've got a molecule of bromine above my arrow. And so when we do this reaction, we know we can use the pi bond as our nucleophile. So I'll have one of those carbons attack the bromine attack back into that other carbon, and we'll kick off our bromide. And when we do this, we know we're going to form a three-membered ring. And in this case, we do want to show dashes and wedges because we are forming stereocenters. And students do get confused with this, and they'll say, well, how do we know whether or not the methyl group is going to be a dash or a wedge and so on? The easiest thing to remember is when you look at your alkene, you see how these methyl groups are cis to one another? And then in the three-membered bromonium ion intermediate, they're also on the same face. It's important to remember that they're going to remain on the same face of the molecule. And it gets a little bit confusing, too. Some students will say, well, why did the bromine only go up? The reality is it can go either on the top face or bottom face of that pi bond, right? So let's draw both of these, and I'll show you what I mean by that. So you would get both of these intermediates. And the reason for this is, let's take a different view of the starting material, and I'll do it more on its side. So I'll draw a carbon-carbon single bond. Our ethyl group is now going back. Methyl group's a wedge. Hydrogen's going back. In this pi bond, we've got these p orbitals sticking up and down, right? And either one of those p orbitals can act as the nucleophilic site, right? So that bromine can go on the top face of that pi bond or on the bottom face of that pi bond. So let's make a note of that. So both sides can act as a nucleophile. Does that make sense? So we do have these intermediates. What's the relationship between them? I'm going to make this smaller. Are they diastereomers and enantiomers identical? What do you guys think? Not quite. So the bromine's still in the same position, so they're not constitutional isomers. But can you imagine, let's just imagine picking this molecule up, moving it down underneath. They're mirror images of one another, right? But they're non-superimposable mirror images. So what would we call that if they're non-superimposable? Enantiomers, right? So we've created a mixture of enantiomers as our intermediate. And then in the next step, we can react either of these enantiomers with our bromide. And this bromide can attack either side. It doesn't really matter. Slingshot this open, but it's important to remember that it does go through the three-membered ring. The bromines are going to add anti to one another. And so for the reaction on the left, the bromine's going to slingshot open like that. The bromine that added from the bottom face. The methyl group is still going to be a wedge, but it's going to kind of flip up. The ethyl group's still going to be off of that dash. The methyl group on the right is still going to be a wedge. And your hydrogen will be a dash. And then for the bottom one, can you see how the bromine is also slingshotting open, but it's going to the bottom now? So you've got a bromine here. The bromine that attacked in is now coming off that top face. We're not changing the stereochemistry, but we are kind of changing the position of all of our groups. We have a methyl, and then we have a hydrogen. So what we've created is a mixture of enantiomers. And just like we saw before, this is a racemic mixture. And it's really important to note, like I said, that these bromines, experimentally we know, are always going to be off of opposite faces of that original pi bond. So you do have to pay attention to the stereochemistry as well. Does that make sense? I know this can feel like a lot. What I would do is try to keep really detailed notes. Go home, review your notes. If you do have questions, immediately come back and ask me, or try to review your textbook. Sometimes the textbook explains things slightly differently than me, and that can be a really good way of wrapping your head around some of these harder ideas. Yep?
Why does bromine attack to that carbon but not the other one?
Honestly, experimentally we can't determine. We will talk about this in a bit more detail. In general, when you have a three-membered ring, where the bridgehead is positively charged, your nucleophile prefers to attack the more substituted carbon. And we'll talk more about that tomorrow, but in this case, it ultimately doesn't matter. It'll give you the same product whether you have it attack the left carbon or the right carbon. Good question. All right, I think we'll hold off there. If you have lab today, remember we are meeting upstairs.